Today, we are diving deep into the absolute bedrock of reality. We're talking about the fundamental building block of literally everything you can see, touch, or even think about, the atom. So let's just jump right in with the biggest question there is.
Really think about that for a second. This screen, the air you're breathing, the distant stars in the night sky, what are they all truly made of at their core? You'd think the answer would be impossibly complicated, but you'd be wrong. It's actually kind of beautiful in its simplicity.
Get this. Everything in the entire known universe, all the staggering complexity and diversity we see around us, is built from what is essentially a cosmic Lego set of just over 100 unique types of atoms. These are the elements. That's the answer.
Now, the name itself, atom, it comes from this ancient Greek word, atomos, which means indivisible. The whole idea was, if you kept cutting something in half over and over again, you'd eventually hit a point where you just couldn't cut it any smaller. But here's the beautiful irony. To truly understand the atom, we had to do the one thing its name said was impossible. We had to split it open.
And this is where the story really takes off. Scientists started to realize that the atom wasn't the final destination. Nope, it was more like a doorway into an even smaller, even more fundamental world of particles. Cracking this so-called indivisible code was the key that unlocked modern science as we know it.
And it didn't happen overnight. It was a step-by-step discovery. Back in 1805, Dalton first proposed that different elements were just made of different atoms. Then, J.J. Thomson found the first clue inside, the super tiny electron. A bit later, Ernest Rutherford figured out that atoms have a dense little center, which he called the nucleus. And finally, in 1932, James Chadwick discovered the last piece of the puzzle, the neutron. And with that, we had our complete model.
Okay, so let's meet the team inside the atom. First up, the proton. You should think of the proton as the atom's unchangeable ID card, its passport. It's got a positive charge, and the number of protons an atom has is what defines, absolutely, what element it is, period.
Living right alongside the protons is the neutron. As you can probably guess from the name, it has no charge. It's neutral. It weighs about the same as a proton, and its main job is to add some heft and act as a kind of heavy-duty glue, helping to hold all those positively charged protons together in the atom's core.
And finally, we have the electron. This little guy is tiny, almost no mass at all, and it carries a negative charge. But do not let its small size fool you. The electron is the real rock star of the atom. It's zipping around the outside, and it's the particle that determines how an atom interacts, bonds, and generally behaves with everything else. It basically defines the atom's personality.
So here's a quick cheat sheet for you. You've got the heavyweights, the positive proton and the neutral neutron, crammed together in the middle, in the nucleus. And then you have those tiny negative electrons buzzing around the outside. The key thing to notice here is the balance. The positive charge of the protons and the negative charge of the electrons are perfectly matched, and nearly all the weight, all the mass, is locked right in the center.
So, how are all these particles actually laid out? Let's work our way from the inside out and take a closer look at the atom's command center, the nucleus.
Okay, so the nucleus is almost impossibly small and unbelievably dense. It's where you'll find all the positive protons and all the neutral neutrons packed in tight. This makes the nucleus the powerhouse of the atom. It's got a strong positive charge, and it contains pretty much all of the atom's mass.
Now, you might be thinking, if the center is so positive, why isn't the whole atom positive? Well, this right here is the crucial part. For every single positive proton locked in that nucleus, there's one negative electron orbiting it. The charges cancel each other out perfectly. It's this beautiful balance that makes a standard atom electrically neutral.
But, that very balance created a massive headache for early scientists. We all know that opposites attract, right? So why didn't the negative electrons just instantly get pulled into the positive nucleus and cause the whole thing to collapse? This was a huge puzzle, the electron enigma.
Exactly. Rutherford's first guess was that the atom was like a mini solar system, with electrons orbiting the nucleus like planets. But that model had a fatal flaw. According to the physics of the time, an orbiting electron like that should be constantly losing energy, which would cause it to spiral inwards and crash into the nucleus in less than a second. But obviously, atoms don't just collapse. So what was really going on?
And here is the genius solution, which came from the physicist Niels Bohr. He realized electrons can't just orbit anywhere they feel like. No, they're restricted to very specific energy levels, or shells. Think of them like lanes on a highway. An electron can jump from one lane to another, but it can never, ever exist in the space in between. This simple rule is what prevents them from losing energy and spiraling into oblivion. Just like that. Problem solved.
All right, now that we've got the basic structure down, how do we actually use it to tell one type of atom from another? You know, what makes gold, gold, and what makes lead, lead?
It all boils down to one single, incredibly important number, the atomic number. And all that is a simple count of the protons in the nucleus. That's it. It's the atom's permanent, unchangeable fingerprint. If you change the number of protons, you literally change the element into something else.
Let's just throw a number out there. How about 17? On its own, it's just a number, right?
Well, in the world of atoms, that number is everything. To an atom of the element chlorine, the number 17 defines its entire existence.
You see, because chlorine's atomic number is 17, we instantly know two fundamental things about it. First, it has to have 17 protons. That's the non-negotiable rule that makes it chlorine. And second, to stay electrically neutral, it must also have 17 negative electrons to perfectly balance out those 17 positive protons. See how that works? It's a package deal.
So where do those 17 electrons actually go? Well, they don't just bunch up randomly. They fill those energy shells we were just talking about, and they follow some pretty simple rules. The first shell, the one closest to the nucleus, can only hold a maximum of 2. The second shell can hold 8. And for our purposes, the third shell can also hold up to 8. They always fill up from the inside out.
Let's actually put this into practice. An atom of lithium has 3 electrons, so the first 2 fill up that first shell, and the last lonely one has to go into the second shell. So its arrangement is 2, 1. Simple, right? Okay, let's try silicon with 14 electrons. 2 go in the first shell, 8 fill up the second, that's 10 so far, so the remaining 4 go into the third shell. Its arrangement is 2, 8, 4. You see the pattern. Finally, potassium has 19 electrons. That means it fills the first shell with 2, the second with 8, the third with 8, and that last single electron starts the fourth shell all by itself. Its arrangement is 2, 8, 8, 1.
So let's just tie this all together. Here's the big takeaway. The number of protons is the atom's soul. It's fixed. It's the atom's identity. That number then dictates the exact number of electrons the atom needs to be stable. And finally, the way those electrons are arranged in their shells, well, that determines how that element is going to behave and react with the entire rest of the universe.
It all seems so permanent, so locked in, doesn't it? The number of protons defines the element, and that's that. But that brings up one final, really tantalizing question. For centuries, ancient alchemists dreamed of turning cheap lead into precious gold. What they were really dreaming about, without even knowing it, was changing the number of protons in an atom. We now know that's actually possible. But that is a whole other story.